just very quickly you can do two things. Whenever I do any of my sample, I always do these two simultaneously. Otherwise, you have to redo it, right? So once you do the image, just pick some area that you can take from the image itself, right? You pick some selected area, then you look at the diffraction pattern. There's nothing. So then the next thing is this thing called the yields. So this electron energy loss spectroscopy. That basically you do in the TEM. So remember I told you when you have this specimen here, so the electron beam, so there's some electron beam directly goes through and some elastically scattered, some maybe inelastically. So if it is elastically scattered, you don't see any change, right? Because energy is not lost. But if it is inelastically scattered, you lose energy, right? So where do you lose this energy to?
To the scattered electrons.
Yeah, so it can be, that can maybe excite some phonons, right? So, or it can maybe emit some electrons from other atoms, right? So some from co-electrons. So you can see a lot of them. Also, you can use it to something called the, if you have a metallic sample, you have a lot of free electrons, right? So then these free electrons, when you have this, this is still, electron is a wave, right? So they can excite this something called the plasmon. So plasmon means if you have a electromagnetic wave, they couple with that free electrons, they kind of oscillate, right? So this is some restoring force. So that means you can lose those electrons energy to plasmons or eventually to remove some electrons from your atom. So that's why typical yield spectrum, if you take, this is also, once you do your TEM image, then you do the diffraction, then you can immediately do this. The only thing you need to have the yield detector, right? We have that one in our system. If you do that one, you see for this energy loss. Energy loss 0 means no loss, right? That means that's the elastic processes, right? Either something that directly goes through or something elastically scattered, right? They all are counted here. That's the most intense peak, right? You get on very, we call the zero loss peak. Then you get some from this plasmon peaks, right? So if you, because that energy is inelastically used for plasmon excitement. So after that you see very low signals. That's why we kind of blow this one. Actually in this real picture it looks like this. So this one, then you have very small signal here. You just blow this part. So that's why we blow by 20 times. Then you see features here, right? These features are mostly coming from this, the electron loss. So from there you can get information about what material, right? What co-electrons are coming out. This is also very nice. That's called the yields. So this has a lot of other, so there's something called the R yields, so very high resolution yields and different things. But everything is on the same thing. You can get information about your material by looking at these peaks. We know from this energy corresponds to what material, right? Okay, so these are the basic things. Here is the EDAX thing I was talking about. So it just scattered light, so you have to have this EDAX detector, right? You can see here, this is how we are looking at this one. When you do that one, you can see this peak corresponding to gallium L, aluminum K, you know this LK, these things. These are basically, everybody knows, right? So how, going from, typically, if your energy states are, you have starting with L then you have K, M, like that, right? So if you have some electron, if you remove from L1, so then where it is coming down, so if it is coming to L, then it is like LP. If it is coming from K, we call the K, because like I said, it's remove this one, where this is coming from, right? So that tells you whether LK or in other this. So here this material has gallium, aluminum, gold, titanium, nickel, all these things. So it's very simple, right? The software can pick up what it is, corresponding energies. So it's a very neat technique to do this one, right? Today when I did my experiment, I saw chromium, selenium, then I saw very huge silicon peak because sample was on silicon substrate, right? Then also oxygen, because silicon has oxygen, right? So I could see oxygen, silicon, then chromium and selenium. The chromium showed two peaks, like one from K edge and other from L, right? So same thing, selenium also from K and L. So this coming from that different orbitals, right? Everybody familiar with these things, right? In quantum mechanics, we are doing L, K, then each one has like SP, DF. Yeah. So these are principal quantum numbers, right? N equal 1, 2, 3. Then you have secondary one, SP. That's basically your the secondary one, right? So L. So I think so. Your first quantum number N can go from 1, 2, 3, 4, like that, right? That's why we have. Then each one can have L, right? So L angular momentum that goes from -1 to +1. Then it can again split into spin, right? So all these things you can predict these things. Okay, so yeah. So next, so that's all I want to talk about, the simple imaging techniques. So let's quickly do something about the other two probing techniques. One is the scanning tunneling microscope. This is very neat. So you can get, actually people, I don't know, have you seen that IBM people using STM, they could move atoms and make the letter IBM with atoms. So this is a really neat technique. So you have a sample, then you have this STM probe. So this is something we call this piezo device. So it can move depending on this roughness. So this works in the quantum tunneling effect. So you have your sample. This is your sample. So then you bring this very sharp tip here. So what happens is this, if you bring this so close, this one has atoms, right? Or electrons. So this one also has electrons. So then the wave function, quantum mechanically we know we represent them by